got episode 11, where we're going to talk about, do transducers between manufacturers have a lot of variation, and how can you start to measure and quantify and understand that variation? So without further ado, we'll talk about the sources of variation first. Then we'll get into what kind of variation you should expect from those manufacturers. So the source of variation of a piezoelectric ultrasonic transducer firstly comes from the piezoelectric material itself. There are many processing conditions in order to produce a piezoelectric material, a lot of different steps. There's also a huge sensitivity on microstructure of the piezoelectric material. Doping and defect chemistry plays a huge role in how the properties end up. So the result of all of that is you'll get variation within a lot, and also variation between lots from a particular manufacturer, much less different manufacturers. So for the same type of device, manufacturers of those devices use similar classes of piezoelectric material, but there isn't particularly one exact standard to achieve a certain property. So the processing, the chemistry is going to have some amount of variability. And I'm speaking again, as I mentioned, mostly regarding PZT, which is the most commercially used piezoelectric material. So that has a ton of variation. It can be plus or minus 20% at the largest extent. So you may expect, let's say, one batch versus another batch of piezos. You take the bottom performer and the high performer from those two batches, you might even very likely end up at 30% difference in properties such as the piezoelectric charge coefficient. The next thing on our list is assembly process and tolerances. Most ultrasonic transducers are assembled by hand. So there are jigs and there are mechanical fixtures in order to reduce that variation, but it will still propagate through your assembly due to human interaction. There will always be variability caused there between assemblers and also between manufacturing sites. And now we talk about transducers being made by different manufacturers, having different steps and procedures, kind of ending at the same thing in the end, but it has the process of how you got there definitely determines what the properties are going to be and how variable their own transducers will be. And the next part about that is tolerances. So physical tolerances, the changes in the length or thickness, those obviously will change the resonant frequencies. So that's something to note. However, the tolerances which really mess up ultrasonic devices are flatness, concentricity, and surface finishes. Those can really change the performance interfaces and make a seemingly good device made with made with components which look good, but maybe there's flatness issues, there's concentricity issues. That can, there's issues with surface texture and roughness that can definitely lead to a failing device out of apparently good parts. The next thing here is elastic materials, and we generally think as elastic materials like metals that we often bond or affix to piezoelectric materials in order to provide a certain function, form, amplitude, gain, horn. There's a couple of different reasons. Those are generally thought of to be more stable than piezoelectric materials. However, their loss properties are also governed by microstructure, which can have variation. So if you need to be very careful about tolerances, or you have the luxury of a low volume item, a low volume transducer, then it is worth your time to continually monitor and investigate the loss properties as well as the elastic properties of the components going into your transducer. The final point here is cables and wires. So cables and wires, they will add inductance, capacitance, and resistance to your piezoelectric element or circuit. So this is really essential to understand these parameters when talking about a sensor or an actuator, in the sense of, we have many sensor applications where there's a wave sent out and you receive something back. That reception back and how it's interpreted by their microcontroller, which then has certain DAC interfaces to it. All that cabling, that wiring is going to affect the received signal, and that's perhaps not something particularly well controlled. So it can lead to variation between swapping out two identical wires, or there may be a batch of cables that come in which are slightly higher capacitance than another batch. These can definitely make a huge difference with small elements. Which in which case the capacitance of the wiring and cabling is significant with regards to the capacitance of the piezo element. So how can you easily detect transducer differences? And the way to do that, so if you have you have a couple of transducers from different manufacturers, let's say you wanted to use impedance analysis, which would be the best thing to do resonance, anti-resonance characterization. But you might be an end user, you consider yourself to be very far down the line, very far away from ultrasonic transducer development. You're very much in the use case. You may not want to invest that money. I would kind of argue against that. Like, you should probably invest if your transducers are going to be a huge part of your project. It's pretty much the core of any device where it is. Most devices that utilize ultrasonics, the ultrasonic function is the core of the device itself. Like an ultrasonic welder, the main thing is the ultrasonic welding, not necessarily all the other manipulation of the workpiece. The heart and the core of it is the ultrasonic welding, and that's the case in many applications. So you do want to take more responsibility upon yourself and do more advanced analysis. So I have a course on impedance analysis if that interests you, and I'll have a link to that in the notes. However, I'm kind of speaking about what you can do today, and that's usually most labs, if not all, have something to measure capacitance, a capacitance meter, an LCR meter, which are very well below the $500 range for a commercial calibratable option. So that can be, so what basically you do there, so capacitance is very closely related to electromechanical coupling in your device. So the higher the capacitance, the same contributors to capacitance are the same ones that contribute toward electromechanical coupling. Now, it's not necessarily a 1-to-1, but those ratios scale very well. So the higher capacitance, the higher performance of your device. So if you notice between different manufacturers that the capacitances are significantly different, they're 25% lower, 30% lower on average, then you will probably could place a reasonable bet. It wouldn't be too much of a gamble to say that yes, the device with lower capacitance that is going to have less performance. It's one sort of indirect way to prove it. The more direct way would be to use impedance analysis, and the kind of very firm way to prove it is to do analytical system level tests, which are probably best suited for the manufacturer themselves to perform, not necessarily the end user. But definitely capacitance and impedance analysis are things that you will be able to easily and quickly implement into your device, device integration effort. So again, my name is Dr. Shakani. I present daily videos, content on answering your ultrasonic transducer and piezoelectric material characterization, analysis, development questions. Leave me a comment and I will get to that question in another video. I'll let you know which video that is. These are all numbered. Answer one question every day. Feel free to send me a message on LinkedIn, send me an email, visit my website, and share the content, and let everyone know that Dr. Shakani is there to answer your ultrasonic transducer questions. See you tomorrow in episode 12, where we're going to talk about a second mode of operation in a radio resonator and what that means. What can you figure out from it? Why is it there? See you tomorrow.